Okay, let's start. For this lecture, I will give you the method called the viscosity Bernstein method, which is sort of independent interest that can be thought of and also can be, um, apply in different settings. I will go with the simplest, the basic setting for the viscous Hamilton-Jacobi equation in the periodic situation. Okay, so let me write out the setting. We consider a possibly degenerate viscous Hamilton-Jacobi equation. It's just let's just do the static problem. So the equation of interest is the static problem with ux plus h of x du. First order term, and then I have the second order term minus trace of ax d squared u equals to 0 in Rn. But as I said, I want to put myself in a simpler setting that everything is periodic, so that I don't have to worry about the boundary or about other situations. And by the end, I'll tell you that in fact, by just using cutoff functions, we can do exactly this argument in a localized way to get estimates. So we assume everything is periodic. So assume x maps to h of xp, x maps to a of x, zn periodic. Okay. Then under some structural conditions, then once you have a solutions, it's unique and hence it's also periodic. All right, so let me write down and also assume the following structural conditions. Let's just put everything together, right? So that I don't have to rewrite it again and again. The first assumption here, besides the periodicities, is that I assume that the Hamiltonian has proper growth. So there exists C naught greater than 0. I'm trying to use as less constants as possible, and m greater than 1, such that I have that our Hamiltonian is superlinear and it grows like p to the m. So 1 over c naught times p to the m minus c naught is less than equals to h of xp less than equals to c naught times p to the m plus 1. Okay, so it grows like p to the m with upper and lower bound is Lipschitz, locally Lipschitz in x. X, y, p constants times 1 plus e to the m x minus y. And we assume also that it's also local Lipschitz in p c naught. So we try to put universal constant c naught. And this holds true for all x, y, p, q. All right. And then the assumption number 2 is that we assume that the matrix AX is degenerate elliptic and has Lipschitz square root. So what do I mean? So AX has a Lipschitz square root. Simply meaning that there is we can write AX equals to 1/2 sigma X, sigma transpose of X, where we have sigma is a mapping from Rn to matrices of size n times d. Okay, for some natural number d. Of course, we already assume that, okay, maybe let's write down. Sigma is Zn periodic. And sigma in L infinity norm is bounded by C naught, and also that d sigma in L infinity norm is also bounded by C naught. So that's what I mean by this. It has Lipschitz square root. The key thing you can get here is that when you take a matrix of size n times d, multiply with a matrix of size d times n, and you have a matrix of size n times n, right? We only get here that A is non-negative definite, and A can have 0 eigenvalues. If you have sigma to be 0, then A is 0. If sigma is identity, then A is identity, but overall, A is quite general. It can be degenerate, it can be positive definite depending on situations. Okay, so those are the assumptions we put. And here's the theorem we want to prove for today. Theorem. Again, of course, under the assumption A1 and A2, and Zn periodicity, then the static problem, of course, it has a unique viscosity solution U. I'm not going to prove uniqueness, but I mean, it's there. The goal for us today is to prove that and there exists a constant L that depends on the dimension depends on C naught, depends on M. No, that's all, greater than 0, such that, and in fact, this constant can be computed explicitly. I'm gonna be vague now, but there is this constant L only depending on those C naught, and the dimension in M is the growth of the Hamiltonian, so that we have our solution is Lipschitz with the constant L. Okay, so that's a Lipschitz result. Of course, this theorem can be proved in other different ways by normal Bernstein method, by adding epsilon Laplacian and do the Bernstein method. But for the purpose of today, I want to give you a proof by using the so-called using the viscosity Bernstein method. Right. Basically, we're gonna utilize the doubling variable method, and we will try to kind of differentiate the equations and do steps sort of along the same line with the normal Bernstein method. But you will see that what we do is really different, because we need to do it correctly in the viscosity framework without smoothing things up. Okay, so we can argue by contradiction, right? So for example, that I will not fix L, but let's say that say for L greater than 0 to be chosen large enough, assume that there exists x naught and y naught in Rn such that we have when I take the maximum, again remember u is periodic and we can in fact bound it later, but let's say maximum of x and y in Rn when we take ux minus uy minus L times x minus y. Let's take the difference. Okay. For L greater than 0, the max always occurs because, again, we are in the periodic setting and x and y cannot be far away from each other, right? Because then the term ux minus uy minus L times x minus y going to be very negative. So max has to occur. And let's say that it occurs at the point x naught, y naught. So this equals to x naught minus uy naught minus L times x naught minus y naught. Okay. If the maximum is less than or equal to 0, then we are done, right? So assume otherwise that this is greater than 0. And our goal is to say that we aim at showing that L cannot be too large. Okay, meaning that if we take L large enough, this is not going to be happening, and hence it means that U is Lipschitz. That's the argument. Okay. So the first thing is that because the maximum is greater than 0, clearly that we must have x naught is not equals to y naught, right? So the easiest thing is to say first that clearly x naught is not equals to y naught, right? Now let's do a little bit of computation because I have the test function or whatever the function in the doubling variable here is L times x minus y, the length, right? So we need to do a bit of computation. So let's do it first. So for the function, let's say call it phi of xy equals to L times x minus y, the length of x minus y. And if x is not equals to y, then we can differentiate, we can compute, right? Then let's compute quickly. If we compute the gradient of phi in x, this simply equal to L times x minus y over its length, right? And as we all notice, this is equals to minus L times y minus x over y minus x, which is minus dy phi of xy. Okay, so it's clear when take the first derivative is symmetric because the function is symmetric in x minus y. Okay. We compute the Hessians in x. You can see that this equals to, if you hit the derivative in the numerator, you get the identity matrix, right? So L times x minus y outside here, identity matrix. If you hit the derivative in the denominator, then you just compute it. You have minus size occur. You have x minus y tensor with x minus y. Here by tensor, I just means that the ij slot is x I minus yi times xj minus yj, right? Maybe I can write that. Okay. Okay, so maybe I can write like here. Z tensor z at the slot ij is just zi times zj. Okay. And similarly, you can compute the other derivatives. For example, d squared of xy, the mixed derivative. You can see that it's exactly the opposite side. So it's minus d squared of xx dxy, right? Because you hit the derivative in y, you have the in the above you have the minus size. Thus, if so, let's simplify our notation. So we set Z is this matrix In minus X naught minus Y naught tensor with X naught minus Y naught over X naught minus Y naught length. Okay, I should have written X naught minus Y naught square, but doesn't matter. Then if I set Z to be this matrix, then we would have that the square of phi at X naught Y naught would be simply a matrix J that can be written as L over X naught minus Y naught outside. And inside I have the block matrix like Z, Z, and minus Z, minus Z. Okay, so this is our Hessian, this function. Okay. Right, so that's the first computation. And now you can see that we are using doubling variable here, right? We do ux minus uy. U is a solution, and hence it's both a sub and super solution. And we are doing doubling variable here. So clearly that we're going to use the theorem of sum or Crandall-Ishii lemma. So by the theorem of sums or Crandall-Ishii lemma. Okay. We get that there would exist a matrix X and a matrix Y that are symmetric of size n, such that ux naught and the derivative dx of phi at x naught y naught and x is in the superjet of u at x naught, and uy naught minus dy phi at x naught y naught, and y is in the subjet at uy naught. And okay, for okay, let me try to be very precise. For kappa greater than 0 small enough, we have 1 minus kappa times the identity is less than equals to the block matrix with the generalized Hessians x and y. 0, 0 here is less than equals to identity matrix minus epsilon kappa times j inverse times j. Okay, and you know, for kappa really small, we can estimate this term. Again, it's not too important, but it can be written as less than equals to identity plus 2 kappa times j, or you can write it just j plus an error term, 2 kappa times j square. Okay, let me say that this term here must be here. We cannot get rid of that, but it's just an error term. We will let kappa tending to 0. So it's there, but it's harmless. Okay. So that's the Crandall-Ishii lemma, that we can control the generalized Hessian in a good way. All right. So now, so far, every single step is just basic computation of the Hessian of L times x minus y, and write down the basic definition of the of what we get from the Crandall-Ishii lemma. There's not yet anything new. What we are doing next is something that we are preparing for the viscosity Bernstein method, that we're gonna try to differentiate the equation in a intuitive way. Okay, so for s greater than 0 to be selected, you can think about the fact that we're gonna, roughly speaking, let s goes to 0 and try to differentiate, although that we will not do that, but that is the moral of the argument here. So I take for some s close to 0, we define a matrix A of S is 1/2. Again, remember the earlier matrix we have. A is 1/2 sigma times sigma transpose. Okay, so sigma times sigma transpose is a correct one. So now let's take A S to be, wait, what? Okay, I might is it okay, yeah, I think okay, it's 1/2. I might mess up the transpose and the sigma, but I think it should be okay. So take S sigma at x naught, sigma y naught. So I inflate the first slot by S, the second slot I keep it the same, times with S sigma x naught, sigma y naught transpose. Okay. So if we compute this, is just 1/2 S squared times sigma x naught, sigma transpose of x naught. Okay, this is just S squared times I. And the diagonal term is going to be the same, S times sigma x naught, sigma transpose of y naught, S times sigma x naught, sigma transpose of y naught, and sigma y naught, sigma transpose of y naught. Okay, so we consider this matrix. We're now gonna multiply AS. Again, this is a non-negative definite matrix, right? We're gonna multiply AS with the inequality above, the trace inequality above, to see what's going on. Okay, so multiply the previous inequality by AS and take the trace. Okay, so what do we have? All right, so let me highlight it. All right, so I have this is the matrix here. It's less than equals to J plus something. That something is small, right? I'm gonna take this inequality. I multiply with this this matrix AS here. Okay, and I'm only taking the trace, right? So clearly that the left-hand side gonna be trace of x multiplied with the slot here, right? Which is S squared times A of x0, right? Because sigma transpose is A times the matrix X. Okay, so that's the first slot in the diagonal. And then the second slot in the diagonal, the lower diagonal, is exactly minus A of y naught times y. Okay, maybe let me remind you. So this part here is A of x naught, and this part here is A of y naught. Okay, so that's what give me the left hand side. It's gonna be less than equals to the right hand side, less than equals to chase. Okay, let's just write it down first. J times AS plus 2 kappa trace of J squared times AS. Again, the second terms here will go to 0 as kappa goes to 0. And let's just ignore it, because I'm going to let kappa goes to 0 after this step. I don't have to compute it. But we need to compute what is trace of J times AS. Okay. Again, remember that J is a given matrix that we computed earlier. J, okay, maybe I can recall. Okay. So recall that J is L over the length of X naught minus Y naught times this beautiful matrix, Z minus Z minus Z and Z. Okay, so I have this is J. Thus, we can just compute, right? So how do we compute? Trace of J times AS equals to just do exact computation, right? L over 2 times the length of X naught minus Y naught times the trace of text block times block. So the first thing would be S square times sigma X naught, sigma transpose of X naught times Z. That's the first slot. The second slot would be minus 2 times sorry, 2s sigma X naught, sigma transpose of Y naught Z. Okay, and that's the second and the third, and then the last slot it just take the lower ones. So plus sigma Y naught, sigma transpose of Y naught times Z. Okay, so that's that. This equals to L over 2 times X naught minus Y naught times trace of, I mean, the first thing can be simplified, right? So it's nothing but S sigma of X naught minus sigma of Y naught times S sigma of X naught minus sigma of Y naught transpose times Z. Okay, so that's that. Let me notice that again. Let's call this one let's call this one M. Okay, so M is non-negative definite. Okay, and let's recall what is Z. Z equals to the identity matrix minus X naught minus Y naught over X naught minus Y naught, tensor with X naught minus Y naught over its length. Okay, that's Z. So it's clear, but let's just do an easy computation. Then if we compute trace of M times Z, it's going to be trace of M, right? Minus the tensor thing. And what is the tensor thing? It's going to be exactly Z of IJ, X naught minus Y naught I, X naught minus Y naught J over X naught minus Y naught square. So this part is non-negative because M, because M is non-negative definite, so the whole thing is less than equals trace of M, right? Okay, meaning that we can get rid of the tensor part. It's not harmful. Thus, as a conclusion, we get the trace of J times AS is less than equals to L over 2 times the length of x naught minus y naught, trace of just M, right, which is S sigma x naught minus sigma y naught times its transpose. Okay, and now we can just compute because this is the trace of this is exactly the norm, right? So the length of S times sigma x naught minus sigma y naught square. I mean the length square. Okay, and what is this length square? Well, we can just use the fact that sigma is bounded by C naught and it's also Lipschitz with constant. What did I say? Let's recall that we assume that sigma is bounded by C naught and it's also Lipschitz with constant C naught, right? So, okay, maybe let's write it carefully. This is less than equals to L over 2 times x naught minus y naught. S minus 1 sigma x naught plus sigma x naught minus sigma y naught or square, right? So by the basic Cauchy inequality and the bounds, this is less than equals to L over x naught minus y naught. The factor 2 goes away. S minus 1 square times C naught square plus C naught square times x naught minus y naught square. Okay, so that's what we have been able to do. So what we have been able to do is to control that the trace of you know J times AS here is bounded by this number, right? Again, remember that S is close to 0, so okay, close to 1, so it's gonna be good. Okay, maybe let me actually even what is this step? 3. Okay, maybe 4. No, let's do still 3. So choose S right away so that it's clearer. Choose S square. Okay, you will see why. S is okay. S square equals to 1 plus beta x naught minus y naught. For beta to be chosen. Okay. So you see that when x naught is close to y naught, this is really tending to 1, right? So if we choose it like this, and we then we notice that S minus 1 square is just a basic inequality that this is obviously less than or equals to S plus 1 square times S minus 1 square, which is S square minus 1 square, which is beta square times X minus Y square. So if we choose it to be like this, then we get, after a long computation, that the trace of J times AS is less than or equals to what C naught square times L C naught square out. Okay. 1 plus beta square times x naught minus y naught. Because one of the x naught minus y naught cancel out with the denominator. Okay, so this is all what we get. And this is really important that we have been able to control the trace, from the Crandall-Ishii lemma. Okay, that's the first thing. Now, okay, maybe let me write a step 4. Step 4, okay, so by step 3, we get, remember the step 3, that I am controlling by this inequality here. I'm controlling this left-hand side by the right-hand side, right? Again, the kappa thing is not important. It will go away. But that means that the left-hand side is really being controlled by the right-hand side, which is trace of j times as, and trace of j times as is controlled by the inequality here, and hence what we get at the end of the day by combining step 3 is that we get that trace trace of s square ax naught of x minus a y naught of y is less than equals to c naught square L 1 plus beta square x naught minus y naught. Okay, so that's what I get. Okay, let me also highlight it. All right. Now I'm going to use the normal viscosity sub and super solution test to write down, and then I'm going to utilize this inequality together with that and to deduce the result. We are nearly done. Okay, so now by the usual viscosity sub and super solution test we have. Okay, maybe I can recall it for you because it has been a long time ago, previously when I wrote it down, right? The first thing I wrote it down was ux naught dx phi xy. X is in the super jet of u at x naught, right? And we can even write down what is dx of phi of xy, right? Dx phi of xy equals to minus dy phi of xy, which is L times x naught minus y naught over its length. Okay. So by this point, what do I have? I have an inequality that ux naught plus h of x naught L times x naught minus y naught over its length minus trace of ax naught times x is less than or equal to 0. Okay, that's what I have. I'm multiplying everything with s squared. Okay, why? Because I want to match with this inequality, right? Multiply everything with s squared. Okay, and then okay, let me also be careful. The second thing is that u of y naught minus dy phi of xy. Y is in the subjet. Okay, then by the viscosity super solution test here, I have u y naught plus h of y naught L x naught minus y naught over its length minus trace of a y naught y is greater than or equal to 0. Okay, so this will also be combined with this. Yeah, maybe let's put boxes around them. Okay. So what do we have? Let's combine the 3 most recent boxes. We can deduce that the trace, okay, let's write this one. On the one hand, C naught square times L 1 plus beta square times x naught minus y naught is greater than or equals to the trace, right? S square a x naught x minus a y naught y. On the other hand, by the 2 latest boxes, this is greater than or equals to s squared times the Hamiltonian at x naught L x naught minus y naught minus h of y L x naught minus y naught over x naught minus y naught. And the u function, and u is easy. S square u of x naught minus u of y naught. Okay, so that's what we have. And now what do we do? I mean, again, s is greater than 1. We're going to take advantage of it. And we're going to use the fact that the Hamiltonian is growing with the rate, with the speed p to the m. And that is a determining factor that helping us to get the Lipschitz bound. Okay, so how do we write it down? Okay, this is greater than or equals to s squared minus 1. H of x naught, L of x naught minus y naught, plus just the Hamiltonian, the difference. Okay, for this difference, we can just control it also by the assumption. And remember that we have u of x naught minus u of y naught is positive. So I'm going to get rid of that. So just the remaining term is s. Okay, maybe let's write it down and get rid of it the next step. S squared minus 1 u of x naught plus u of x naught minus u of y naught. Again, this is assumed to be greater than 0. We're going to throw it away. Okay, so maybe let's imply. So this implies the c naught square L 1 plus beta square x naught minus y naught is going to be greater than or equals to. Okay, remember, okay, we chose, okay, let's write s squared minus 1 first. We have that. Let me show you again the assumption for a couple of seconds so you remember. We assume that our Hamiltonian grows with the speed p to the m. We assume that it's Lipschitz, locally Lipschitz in x. And we assume that it's also locally Lipschitz in p with all the specific constants. So now we can write down that the first term is going to be greater than or equals to 1 over c naught p to the m. P here is exactly L, right? So L to the m minus c. Wait, let's write it carefully. Minus c naught. Okay, and this is the winning term. This is a determining term that helping us to get the Lipschitz bound. And other terms, minus, okay, I'm gonna take the worst case scenario for other terms, c naught times L to the m plus 1, right? Because that's p to the m times x naught minus y naught. Okay. And I'm throwing the other terms away, the last term away, so just s squared minus 1 times u of x naught. Okay. And now recall that s squared was chosen to be 1 plus beta times x naught minus y naught times the length. Thus, if we plug this one in, we get what? We get c naught square L 1 plus beta square. The length of x naught minus y naught is greater than or equals to beta times x naught minus y naught. Okay, let's pull beta in. X naught minus y naught as a common term. Beta over c naught L to the m minus beta c naught minus c naught L to the m plus 1. Plus beta times u of x naught. Okay. what is interesting here is that you see that there's a competition of this beta over C naught L to the M and C naught times L to the M. But beta is about choice now, right? So we can choose beta in such a way that beta over C naught is greater than C naught. So pick beta over C naught to be, let's say, C naught plus 1. That is beta is C naught times C naught plus 1. Then, you know, we handle this term it's gone, right? Then we have, and we now going to cancel out x naught minus y naught. So C naught square L1 plus beta square. Wait, beta is decided. So beta C naught square, C naught plus 1 square. It's a lot of constant. It's greater than or equals to L to the M minus C naught square C naught plus 1 minus C naught plus 1, just constant, plus beta times U of x naught. Okay. I kept this term here to the end to show that U does appear when we do local estimates. We do need to have the L infinity norm of U plays a role in the bound. But this is, you know, we in our case we assume everything is periodic. So recall the static equation Ux plus h of x du minus trace of a x d square of u equal to 0, right? This was our equation. And you can see that if you pick a constant, and because of our assumption, we have that minus C naught is less than or equals to h of x 0 is less than or equal to C naught. And this implies that exactly minus C naught and C naught are a sub and a super solution to this equation, right? So we have u in our infinity is less than or equal to C naught. Okay. So now I'm going to replace it as well. So it's going to be another C naught square times C naught plus 1. Right. So overall, what do we get? We get a lot of C naught, but so as a result, we yield that C naught square L 1 plus C naught square C naught plus 1 square is greater than or equals to L to the M minus C naught cube. Okay, let's say 2 times C naught cube plus 1 or something. Yeah, something like that. Yeah. Okay, I might be a little bit not careful here with all the C naught, but I'm just some C naught. Okay, so we have this inequality, and recall that M is greater than 1, right? So you can see that if L is getting to infinity, the right-hand side is going to be growing faster than the left-hand side, and hence by some tedious calculation, you can compute how does L depends on C naught, but this implies that L has to be bounded. Be not too large, right? Okay, so we come back to our assumption here. We were saying that, okay, if the maximum is going to be greater than 0, and a 10 at x naught, y naught, and L cannot be too large. And hence, what it means is that here, if we select L to be large enough so that this inequality, the red one, is wrong, then that cannot be the case. Because as a conclusion, we get that hence for L large enough. And you can see that it's clearly only dependent on the dimension C naught and M, right? We do get that the maximum of X and Y, Ux minus Uy minus L times X minus Y has to be 0, right? It cannot be positive. And what does it mean? This implies that Ux minus Uy is always less than or equals to L of X minus Y. It is symmetric. Sorry. So this is true for all X and Y. And thus we get our result. So what's the point here? The point I wanted to say here is that we are not doing any differentiation here, but we are doing it implicitly through letting S going to 1. What we are choosing here is that we are choosing S is 1 plus beta times X naught minus Y naught, right? And by choosing it this way, when, roughly speaking, when X naught minus Y naught going to 0, then we are roughly speaking taking the derivative along this sort of direction, and hence it fits with the sort of philosophy of the classical Bernstein method. That's the first thing. The second thing that it fits with the classical philosophy of the Bernstein method is that we are using the growth of the Hamiltonian. And in this case, the most important term is, in fact, the term 1 over C naught times L to the M. And this growth of the Hamiltonian comes back in the Bernstein method and helping us to get the gradient bound. Okay, and that's the end of the story. So let me give the final remark is that this approach works also for local estimates. We actually don't need to assume any periodicity or stuff like that. The argument is pretty much local. You can just need to work on, let's say that for X and Y in the ball of radius 1, for example. And in order to do things, you can, instead of just taking Ux minus Uy minus L times X minus Y, you can also subtract something that sort of growing to infinity at the boundary, and we can get about the Ux minus Uy is less than or equals to L times X minus Y. And here, L depends on C naught, M, N, and also the L infinity norm of U in, let's say, a bigger ball, B2. For all X and Y in B1. Okay. The proof goes in exactly the same way. It's just a bit more tedious because what you really need is that you need to use also a function that blows up at the boundary. Okay. So that's all. Right. Thank you.